Well, welcome everyone. We're very pleased today to welcome our guest speaker, Samantha Thompson from the Lowell Observatory in Flagstaff, Arizona. Samantha is Lowell's curator, which means she manages the observatory's historical artifacts, and she also designs and manages their scientific and historical exhibitions. Samantha holds a BA in physics and astrophysics from Berkeley and a master's in history and philosophy of science from Imperial College in London. She has held internships at the National Air and Space Museum in the Division of Space History and worked at the National Maritime Museum and Royal Observatory in Greenwich. She subsequently worked in astronomy programming at the Santa Barbara Museum of Natural History and in youth development programming at UC Davis. She joined Lowell's staff in 2012. Samantha is currently a Ph.D. candidate in the history and philosophy of science at Arizona State University. Her research centers on the development and use of electronic image intensifiers in astronomy during the 20th century. Now, central to that story is the Carnegie Image Converter. I can show you an example of one of those here, if you're interested. There's one in the exhibit case out in the hall, but this is a naked one where you can actually see how it works. It's a cascaded photomultiplier tube that was developed at it was developed in a multi-institution effort spearheaded at DTM in the 1950s and 60s. You're welcome to take a look at this. I know this device personally because, not this one, but this type. As an undergrad in the 70s, my college observatory had a very modest telescope, a 24-inch reflector. But we had a Carnegie Image Converter on it, which meant that was effectively a 2-meter telescope. And you could do real science with that. So it's exciting to have come to the place where this was invented.
And where was that 24-inch telescope?
That was at the University of Rochester.
Rochester?
At the
Okay.
Mcgee Observatory.
Well,
Yeah.
big optics place.
So, yeah, that's right. That's right. But significantly, this is the device that enabled Vera Rubin, Kent Ford, and their colleagues to obtain the galaxy rotation curves that led to the recognition of dark matter in the universe. So this was a seminal advance, but it's largely forgotten technology today. It had a fairly brief heyday. So I'm really pleased to see this work finally get the attention of a professional historian. As far as I know, Samantha is the first person to really take a scholarly look at the documentation of this technology and its use in astronomy, and we really appreciate the opportunity to have her with us today. So Samantha's talk is called Television as an Aid to Astronomy, the Rise and Fall of Image Tube Technology.
As seen on TV.
And live in person.
There you go. Can everyone hear me? All right, thank you. Thank you so much for having me today. I really, really appreciate it. I'm here for about 3 weeks in the archives, going through lots of old correspondence and documentation, so I'm learning a lot while I'm here. I will say this is definitely part of my dissertation. I just advanced to candidacy in the spring, so I'm really digging into it. So my point is, think of this as a works in progress talk, okay? For people who lived through this technology, that have insights, I'm definitely at that stage where I welcome input and suggestions of places to go. So,
Is this at Northern Arizona University?
this is through Arizona State.
Arizona State, all the way down to Tempe.
Yep.
It's a long way.
Luckily, I don't have to go down there ever. So we have Skype. That's how I communicate and make it work. So there are 2 things I want to accomplish in this talk. The first is to discuss image tubes, a technology that struggled to gain acceptance by the astronomical community, despite the many advantages it had over the competing form of imaging, which at this time was photography. If you go to the Griffith Observatory in LA, they have a small exhibit that kind of chronicles imaging and astronomy. It goes from, Galileo sketching to photography and the CCD. And somewhere in this story, image tube technology got lost. So part of this driving is, why did this technology that really produced a lot of wonderful science gets ignored to this day? My degree is in the history of science. I tend to focus on the history of technology, and I'm especially interested in issues of technological choice, technological failure, and the borrowing of technologies across disciplines. So I also want to discuss a little bit about this field to kind of give you guys some background as to what it means to get a Ph.D. in the history and philosophy of science. Most historians of science and technology have backgrounds in science. You'll find that a lot of them did their undergraduate work in science. So it shouldn't be surprising that the way that they analyze the past is similar to the way that they would analyze scientific data. In doing this, besides just trying to get the word out about what it is I do, hopefully this will help put this technology in this era of history into more of a social context for everyone. All right, so a little background. So you have two major areas of technological progress have been responsible for most of the modern advances in observational astronomy. You can either have bigger telescopes to gather more light, or you have better detectors. Early astronomers sketched what they saw, drawing only what their eyes could detect. In the late 19th century, readily available dry, gelatin-based photographic emulsions really revolutionized the field of astronomy. Photography not only provided a permanent record, but also allowed for integration over extended exposures. In 1910, photoelectric principles were exploited to measure stellar brightness. The accuracy of this method far exceeded that of photographic methods. The disadvantage of the photoelectric technique is that only one measurement could be made at a time, whereas a single photograph could measure multiple brightnesses in the same area. To overcome this disadvantage and take advantage of the benefits of the principle, experiments began into the photoelectric detection of astronomical images. Here's the first part of an article in the New York Times in 1934 called The Electronic Telescope. In this brief article, the author describes a 200-inch,
I think Mount Wilson's 100-inch, not 200.
So this is the telescope that was going to be built at Palomar, but at the time it would have been referred to as Mount Wilson, since Mount Wilson was coordinating. No worries, I get that question every time. So it's also the New York Times, so you do what you can with journalists.
We also solved the problem of multiple observations by building multi-channel instruments.
Right.
Where the light was divided and sent through 3 or 4 apertures with different filters.
Yeah, so that technology kind of came along as image tubes being developed at the same time. So even before the completion of the Palomar 200-inch, astronomers at a AAAS meeting discussed an electronic detector based on a television-type camera, which they said if mounted to the 200-inch telescope would create the equivalent of a 2,000-inch mirror. This wasn't the first time the use of television technology had been discussed for use in astronomy, but it was the first time a technical method had been offered. The potential of this technology was really exciting, as you can see in the article's discussion of, and I quote, Mars and its canals, projected as a disk a foot in diameter, the frontiers of the universe pushed out several 100 million light years, stellar distances measured with an unheard of accuracy, new revelations of the structure of the great nebula in which we live and call the Milky Way, the vistas opened are endless. So, very poetic way of saying there's a lot of potential with this technology. However, the article does go on to question the trustworthiness of these electronic signals. It asks, is an apparatus that converts starlight into electricity and electricity into a visible image just fabricating a reproduction, and should this reproduction be trusted? The doubt seems to lie in a deeper misunderstanding of the physics employed in this method and the technical skill needed to operate such devices, but it wasn't uncommon to question the usefulness of a new technology. Astronomer Joel Stebbins, who I'm sure many of you are familiar with, pioneered photoelectric photometry. He acknowledged these competing views of hope and hesitation in the 1943 address to the AAS. He raised the issue of the law of diminishing returns in the field of astronomy, and you'll see this in many sciences, and asks what it takes for astronomers to accept a new technology. A telescope twice in size might cost 10 times as much to build, and the resulting gain in power is not necessarily proportional to the size or cost. He argued that if offered the money for a 100-inch telescope, many astronomers would have, and I quote him here, the moral courage to say that they prefer to build an 80-inch telescope and use the remainder of the funds for additional instruments and for better operations. I'm sure many people would continue to do that today. He also proposed the question of whether longer photographic exposures resulted in enough gain to make them worthwhile. Is a 4-hour exposure worth the extra time over an exposure that is 15 minutes shorter? Is an instrument that provides a slight higher gain in efficiency but cumbersome to use, like image tubes, worth the extra return? A bigger mirror, longer exposure, and advanced instrumentation have all provided advances in astronomy, but the law of diminishing returns seems to prevent some from trying something new. The hesitation to adopt new technologies was spurred on by a social change in the field of astronomy. When you have astronomy, physics, and engineering beginning to meld together. Caltech astronomer Jesse Greenstein called this the de-astronomization of astronomy. Greenstein later called acknowledging that while astronomy had typically been done by a small, isolated group of astronomers, the relatively recent inclusion of new instruments and observational aids had begun to blur the line between astronomy and physics. And you see this throughout the history of astronomy, points where, chemistry had begun to be part of astronomy, later geology and biology.
He pronounced his name Greenstein.
Greenstein.
Just a little tidbit.
Okay. In a 1982 interview, he said, "Years ago, astronomy was done by looking through telescopes by astronomers. Later, it was done with instruments, some of them invented by physicists and used by astronomers. Now there are instruments invented by physicists and used by physicists who like to call themselves astronomers. There are even physicists who work on astronomical topics from space and call themselves physicists. So we've gone historically from being an isolated small group to being an integral part of advanced physics in almost every field." With a surge of new technologies and an overlapping of disciplines, astronomers were forced to either learn new skills or begin consulting with trained scientists from outside their field. Either way, astronomers were required to adopt new techniques in order to utilize the newest and best ways of observing. This trend can be seen from the introduction of photography in astronomy, photoelectric photomultipliers, and the dominance of CCDs by the last quarter of the 20th century. But the question I ask as I move through my dissertation is how eager and willing were astronomers to accept these new technologies into their way of life. So there's a curator at the Air and Space Museum who's done a lot on the history of photoelectric photomultipliers, and he wrote, "Underlying this narrative review is the assumption that astronomers have always sought out better ways to practice their art. We will not test this assumption here, though it would be useful to do so, especially in areas where new technologies required extensive training, the migration of technical talent into astronomy, and a fundamental reorientation of the size and scale of research." So through my dissertation, I hope to consider this assumption that astronomers always seek the best ways to practice their art and review a technology that really struggled to gain acceptance by the community, despite the advantages it had. Because image tube technology did not outlive its competition, there are some places where image tubes are still used, but very, very few of them. It's often seen as a failure, a waste of research time, and not equipped to satisfy the current needs of astronomers.
And there are some astronomers now who are really good at designing and building instruments. Jim Gunn is one.
Mm-hmm. Yeah, instrumentation in astronomy has really taken off since this period. You can see this as kind of this kicking off point of that development that we see now.
And in many other fields of physics as
Can we
well.
let her continue with that or not?
I'll note that this is not unique to astronomers or scientists in general. It's easy to assume that technologies that reign supreme today do so because they are considered the best. However, it might be more suitable to what historians of technology call the path-dependent view of technological choice, where the reasons for a specific choice are less obvious. The common perception that the surviving technology outlasts competing technologies simply because they are better really doesn't survive critical examination. By examining those technologies that lost, we can uncover deeper reasons for technological choice and learn more about the community that made that choice. So as an example, consider the development of the automobile. The electric, gas, and steam-powered car were all developed at roughly the same time at the very, very end of the 1800s, beginning of the 1900s. This is an electric car built in 1902. Historians argue that the triumph of the gasoline-powered car was not inevitable, but due to the cultural construction of these technologies. There was a nexus of factors, including cultural. For example, electric cars were underpowered and less rugged and apparently more feminine at the time when most car buyers were men. You have structural factors, including the shortcomings of battery life at the time, and systemic factors, like the time needed to charge a battery is a lot longer than the time needed to fill up a tank of gas. Historians argue that the flow of ideas and innovations among builders of bicycles, cars, trams, and all forms of car really provided competition that stimulated improvements. Ultimately, the electric car contributed much to the design of the gasoline-powered car, including the gearing systems, cord tires, and electric starters all came from the electric car. Although the electric car did not beat out its rivals, part of its design can be seen in that triumphant vehicle. And you can bring that forward to today. We see the same cycle. The electric car has been introduced throughout the 20th century, and it's kind of been swatted down for different reasons over time. So it'll be interesting to see at this point in time what allows it to succeed. My point is that you can't judge a technology simply based on its components alone. By placing focus on the user instead of the builder or the technology itself, you reveal new insights into the decision-making process. An early 20th century astronomer, the user was also the manufacturer and builder and designer, so you get this a lot more in astronomy. So through my dissertation, I addressed the theme of technological choice with regards to the adoption of two-dimensional imaging technologies. From about the 1930s through to the mid or late 1970s. Given the hope and enthusiasm for this technology, from its earliest conception, like that described in that New York Times article, this method was positioned to gain a much wider acceptance and a longer life. And despite active development, as you can see through the science it produced, as a whole, the community was hesitant to adopt this technology. So I'm going to go through a few major episodes or places where part of this development was either promoted or developed or used. The first I'm going to talk about is television and military research. So the developers of television were the first to really apply the photoelectric effect onto two-dimensional imaging. Commercial industries used professionally trained physicists to run their television development labs. Research was highly competitive and secret at this time. During World War II, these same physicists were used in efforts to build television-type detectors that could detect heat from enemy planes. So you have exhaust coming out of a plane using infrared, and using these detectors you could detect where that plane was. Ultimately, development in these two fields provided astronomers with the confidence needed to attempt to utilize the same systems in astronomy. And these advances, really what they did is they showed that there was a need for a better detector. I will say, as I go through archives for various places, these are the hardest archives to get a hold of. Places that were run in commercial labs and through the military. A lot that we don't know about this time period. So in 1951, an astronomer in collaboration with the Cambridge observatories, carried out tests with a standard television camera tube that was called the Image Orthicon to ascertain any advantages over photography alone. Do I have it? That one on the top right is an Image Orthicon tube. Your random fact of the day is the Emmy Awards that are held annually to the best in television are named after that tube. When the Academy of Television Arts and Sciences got together, they created an award, and originally we were going to call it the Ike, which was named for another camera tube called the Iconoscope, and decided to call it after the Image Orthicon, whose nickname was the Emmy, and they feminized it to Emmy, so you should learn something today. Initial results using the moon as a subject were very encouraging. Direct comparison of the two methods, as you can see in these images, shows the enhanced contrast of the image by the television technique, and greater detail can be seen in the television produced image. So the top image is the moon recorded by direct photography at an exposure time of 4 seconds. The bottom image is the moon recorded with an Image Orthicon with an exposure time of 0.2 seconds, and then it was photographed off the television screen. Greater detail can be seen in the television produced image, largely due to the allowed shortened exposure, which decreased some of the seeing effects. Quantitative tests were performed, determining that television was also superior in sensitivity, resolution, and efficiency. Early experimental work with television camera tubes proved to the astronomical community that television systems could be employed to the benefit of the astronomer. The promising results of these tests encouraged the community to test further, design, and build electronic detectors that they could routinely use at observatories. They figured that the most beneficial device would employ the advantages of the standard television tube, but would be adapted to the low light levels needed in astronomy. If you can picture television studios, we have a lot of really bright light, so the needs of astronomers are very different than what the commercial companies were being produced. Some astronomers attempted to build original tubes for very specific purposes, but television camera tubes did remain the preferred choice for several years. So the results of these really piqued the interest of Bill Baum, who was an astronomer at Mount Wilson Observatory. Spent a lot of time out here in the late 1950s and 1960s. But in 1950, Bill Baum spoke to Ira Bowen, who was the director of the Carnegie Observatories. Excuse me. That he said that future observations would be made with fast electronic devices rather than photographic plates. Baum was hired to produce this equipment. He started off building photometers or utilizing photometers to great success. Baum wanted to develop two-dimensional devices to replace, again, the photographic plate, and he initially began testing these television camera tubes. This is Bill Baum here. This is my favorite photo of Bill Baum. You guys have lunch club at Lowell. We do funny hat staff parties, so that's Bill Baum. A very, very serious astronomer, so this was unlike him to be wearing this. He had a lot of success evaluating different devices and determining their limitations. In the end, he decided that the commercially produced tubes weren't good enough. The problem, again, is that they're designed for really high light levels, not the low light that astronomers require. Also at Mount Wilson at the time was an astronomer called Bill Livingston, and he had gotten interested in using the Image Orthicon. He moved to Kitt Peak Observatory and started using them there, but was eventually told by the director, it's time to move on from testing and you need to produce science. Astronomers had begun to accept the limitations of television tubes and sought to design tubes for their needs. Stebbins started writing to RCA and Vladimir Zworykin, one of the inventors of television, and Bill Baum approached EMI, basically the English version of RCA. He was put in contact with a physicist called Jim Mcgee, and Mcgee had built the first working television system in England. So you have these astronomers seeking out specialists in their field. Jim Mcgee had been at EMI for 20 years working on television and photomultipliers. During World War II, he worked on war projects and had a was largely involved with these trying to detect exhaust from coming from enemy planes. Baum invited Mcgee up to California for an observing run, and Mcgee was hooked on astronomy. He loved it. They agreed that the next step to take an electronic detection would require the facilities at EMI, but unfortunately EMI was not interested in really giving over Mcgee's time to this project. So this is one of the big themes that I start to see throughout this project is astronomers, scientists. It's a very small group, and specifications and what everyone's needs are extremely limited. So it's hard to get big companies to find the consumer base there to go ahead with this work. In 1954, Mcgee decided to move away from industry and into academia, and he became the head of instrument technology at Imperial College London. There, he established a group to work on photoelectric devices that appeared to be required for scientific purpose. He realized that in here, special tubes of this type were required, but in such small numbers that commercial laboratories were not interested to develop or make them. Mcgee had already begun developing these two different methods to realize the advantages that he was seeking out, one employing a method called electronography, and the other using image conversion or intensification. So one of those methods, electronography, was first suggested in 1938 by a Paris Observatory astronomer, André Lallement. As early as 1936, he predicted that from quantum efficiency considerations that gains by a factor of 100 over conventional photography could be obtained by using the photoelectric effect. And he spent about 15 years working on photomultipliers. Not satisfied with these, he worked towards an electron camera he completed the first one in 1951. This system is when you have photoelectrons are directed to impact an electron's sensitive emulsion, is what I refer to as electronography. Subsequent work was devoted to improving the performance and reliability of the electron camera. Lallament's system had the benefits of very high definition and was also very light, so it could be placed at the primary focus of a telescope. It was acknowledged at the time that the preparations of the camera for the night's work were lengthy and laborious, as it was called. This is partially because the photocathode was destroyed after each use. So this is a diagram of this camera, and you'd actually have to break the glass to get at the photoelectrode. So this wasn't an easy process to get it ready for the next night of observing. Lallement worked closely with Merle Walker and Jerry Crone at Lowell Observatory. They produced a lot of great science with this method, but not many astronomers were interested in the work required to actually handle this instrument. One of the problems that these astronomers who had early interest in this technology was getting word out about the technology. So in order to spread the ideas and benefits of image tubes, Mcgee organized a symposium on photoelectric image devices. It ran several times throughout Mcgee's life and grew, but didn't quite gain. Mainly the people that came were physicists, so you had people actually building the technology, and there wasn't a whole lot of interest from working astronomers at the time. So that's where Carnegie comes in. So like I said, there are three main types of image tubes. You had signal generating, which are these television tubes, electronographic, and phosphor screen output tubes. So my dissertation largely focuses on those phosphor screen tubes that were developed at and under Carnegie's DTM. When Bill Baum showed interest in developing image tubes from astronomy, Director Bowen thought that such developments would be too difficult and expensive for Mount Wilson. So Baum appealed to Bush, who was president of Carnegie at the time. In 1954, Bush created a committee which had 4 members representing 4 institutions. It was Bill Baum from Wilson. He later moved on to Lowell Observatory. John Hall was at the U.S. Naval Observatory, also later went on to Lowell Observatory. L. Martin was at the Bureau of Standards, and Merle Tuve at DTM. Carnegie was given a $50,000 grant from the Carnegie Corporation to get started, and this was not to cover overhead. It was primarily focused on building a prototype, getting tubes built. Baum worked with Kent Ford at DTM and then took a leave of absence and went to England to work with Mcgee for a year. So he was extremely hands-on. He was the only member of this committee that was located on the West Coast. They spent a lot of time here and a lot of time in England. The committee decided at the start that they needed an astronomer they needed to develop a tube for an astronomer, and that an astronomer could not be expected, and I'm quoting Baum here, could not be expected to operate a highly technical physics experiment at the telescope. So they ruled out the Lallement approach. The image tube, they decided, could not be more difficult to employ than an additional lens system and must be manufactured commercially. They couldn't expect a university or a private lab to keep up with production. They thought competition between companies would produce a better tube that could be produced in a university lab also. And they suspected that they would have to rely on these private labs to get things started, though. They contracted the development to companies with electron-optical capabilities and tested their experimental models in laboratories and on telescopes, mainly at the Naval Observatory. Vera Rubin was added to the project in 1965 when Merle Tuve decided that the future development needed the guidance of an astronomer. Rubin planned observations of galaxies, which were objects of sufficiently low light brightness to challenge the capabilities of the Image Tube project. One of their reasonings for adding Vera Rubin onto this project was also that astronomers feel like they were a part to figure out where tubes were used most often, and how happy or what hesitation was there at the actual observatory in using them. Besides that $50,000 fund from the Carnegie Corporation, this project was eventually funded by the NSF and got millions of dollars over the courses of 15 years to fund the project. And again, this was to build tubes, to produce tubes, to give out to astronomers. So in completing the research for my dissertation, I'm looking to address the questions: what role did the Carnegie Institution, specifically this committee, have in the development and promotion of this technology? Why did they decide to explore this technology? And why did they choose DTM as a place to headquarter that? One of the things I've come across so far as reasons that tubes weren't used has come down to disciplinary differences. So what I've discovered talking to astronomers is people that were studying solar system objects, people that were studying the sun, had no interest in going, this is the law of diminishing returns, they had no interest of going through this extra process when they had a really bright light source. When you started studying quasars, when you started studying distant galaxies, suddenly this interest peaked. Because again, we weren't building bigger telescopes through the middle of the 20th century, so you needed some better detector that could gather that light for you. The other big issue is standardization and commercialization. So the Carnegie Image Tube Committee really struggled to find a company that would produce a tube to the level that astronomers needed it to be. There were also issues of astronomers wanted tubes to very specific specifications. So you had different wavelengths that they wanted to study, and commercial companies just couldn't produce these in the small quantities that astronomers wanted. I think another big issue that I'm finding now is the promotion of it. The word wasn't getting out. amongst the community to the extent that the Carnegie Committee thought it was. So there's a lot of work left here to do. I've learned a lot since I've been here, but it's definitely a lot of questions that are left to be answered. So that's what I have for you guys today. Thank you very much.
Still have a box of those tubes at home?
Really?
Don't know what to do with them.
I'll take them. I'm sure Sean would too. Yeah.
It's hard to get though. I have an old Fisher tuner that uses tubes when I need a replacement on the place. And they were made in the USSR.
Yeah.
It said RCA on the box. So you look and see who made it.
That's really interesting. Yeah.
So where did the phosphorus come, or the idea for the phosphorus come from? Do you know that?
I don't know, but I know that this was largely because of Kent Ford's work as a graduate student. Had kind of gotten into this and brought that interest over. I don't know though.
So Samantha, you talked about in your discussion of technological choice and electric car as an example. I can see how in a consumer product these social and cultural forces would be important variables. But how do those factors work in a technical field like astronomy?
Well, you think it's special, but it's really not. I mean, we're all, at the end of the day, guided by money, where we can get funding from. But you see this and that's where I see it the most, is the small group of consumers that scientists make up. And I use the example of Blu-ray versus HD DVDs. There was, which way we were going to go. At the time, I thought they'd go with HD DVD because it just was a common name, not realizing I wasn't a gamer. I didn't use Sony. So you already had the Sony consumer group there that helped spur on the Blu-ray group. And if the problem is there just isn't interest as well, that really can affect the direction that it goes.
Well, your observation, and this was surprising to me that you said that getting the word out. I think of the astronomical community in the 50s and 60s is very small. Like everybody knew everybody kind of thing, and clearly that was not the case. Yeah.
No, and I mean, you had started studying such unique things at this time because of what the 200-inch allowed you to study. I mean, both advances in instrumentation and technology really allowed you to go farther into the universe, so those fields really started diverging at the time as well. Yeah.
What kind of efforts was Carnegie making to sort of share with the community? I mean, back then, how was that done? And how is that done nowadays? Because I think this is a problem that, is an ongoing one. People sort of assume that we all know what everybody else is working on.
Yeah.
It's getting harder and harder despite having more and more media outlets to
Well,
share.
and it may have been done on purpose in a way. So Bush was really specific about, he didn't want this to be a Carnegie project. They kind of controlled and dispersed money, but this was a collaborative group. And he told the committee members, it's your job. Get the work done, get the word out. There was the yearbook that there was always an article in. There was a lot of articles written, even in Sky and Telescope, some really common journals. I don't know. It's really confusing to me because I see all the articles in AJ produced, and yet astronomers, this was unheard of from them.
Were there not presentations at meetings or...
They did present at AAS meetings. Kent Ford went to quite a few. I wonder if how many of this was interpersonal issues. Jim Mcgee, who was at Imperial College London, was not liked at many of the observatories here, and if he's the one pushing this technology and you're turned off by him, there's a lot of lectures to go to at conferences, and you're going to choose one or the other. I don't know what you do today.
Well, did any of the astronomers at Mount Wilson or Palomar adopt using image tube technology?
Absolutely, and that's a really funny story. I was giving a colloquium at Lowell a few weeks ago, and I had two astronomers in the group who both worked at Mount Wilson and Mount Palomar in the 1960s, early 1970s, and they were adamant that this technology was loved. It produced the greatest science ever. So it did infiltrate the Carnegie observatories. It did get used extensively by them. But this is part of my trying to pick out who chose to use it.
I mean, what fraction of the papers, I guess, published in 1965, say, used electronic detectors versus standard photographic?
A really small proportion, though. Do I have that number here? I did do a search through ADS to see how many times the Carnegie Image Tube had been used. I remember it was something in the 700s over a 50-year span. So it was used often, but by just a few observatories.
I have lots more questions.
Other questions?
Nancy, yeah.
When we were starting the planning for the Space Telescope, the Hubble, we had decided that we would use the image tube, and we put a lot of money into it, and a lot of time and effort, and it was just not possible to build one that would do the job. The problem was that the Space Telescope wanted the ultraviolet, and that meant a quartz window. But melding the quartz, attaching the quartz window to a metal tube turned out to be impossible. And so when Westphal came along with and suggested that the CD could work with an image, chemical image wavelength converter, that was the end of the image tube.
Exactly. And I try not to get into that in my dissertation, focus on the end, but I do consider the Space Telescope the end of the image tube era. It was that decision. And there's the book that Robert Smith wrote about that work is just fantastic in detailing that decision, if anyone is more interested in that episode. But it was, and it also, because it was we wanted technology that we have currently. So there's a lot of interest. That was the Vidicon, I believe, that they were using.
There were also advantages in the CD in the sense that the image was much more stable. It was much more linear. The two-dimensional part of the image was much more stable.
And by that time, Bill Baum, who was at Lowell Observatory, was on these Space Telescope committees, and he had gone full steam ahead with CCDs. So the people that were really promoting this technology were they weren't holding on to image tube technology for any nostalgic reasons. They were interested in what technology could get them the best results. So they really quickly jumped on board. So no one would argue today that we use CCDs over image tubes. But yeah, that's a really important episode that kind of concludes the story.
So were these same companies using image tubes for filming?
So you used these image tubes for television, but it was also used for different areas of science. So the Atomic Energy Commission was really interested in developing image tubes also, but again, they had different requirements.
So never for filming movies?
I don't know. Yeah, I actually just wrote a post-it this morning that said, what else was RCA doing? So you would think that eventually would get moved over to film or to movies, but...
I think movies was one area in which photography actually did fairly well up until recently, actually. So maybe that has something to do with it.
Well, Samantha will be working in the library this afternoon. If you'd like to stop by and chat a bit, that would be great. And I think she'll be here part of next week as well, continuing her research in our archives. But let's thank her for a really fascinating...
Thank you.